everyone. In our second video on making sense of your world with statistics, we will focus on the topic of standard deviation. In our last video, we saw that mean, median, and mode can provide helpful summary information about data, but that a single value is limited in what it can convey and can even be misleading. For instance, we looked at the two data sets that we see here and computed that for both of them, the mean, median, and mode are all 10. However, a visual of the two data sets shows just how different they actually are. Additionally, we saw an example with housing prices where the median gave us some information about housing prices but didn't tell us anything about the spread of the data. Are most of the housing prices clustered close to the mean, or are they spread out over a wide range of prices? We discussed one way to describe the spread of data called the 5-number summary. And in this video, we're going to focus on a second way to describe the spread of data, the standard deviation. The standard deviation is a measure of how much the data are spread out from the mean. So the smaller the standard deviation, the more closely the data are clustered about the mean. Here's our formal definition. Suppose that x1, x2, all the way up to xn is a list of data values with mean x bar. Then the variance is defined to be the sum of the squares of the differences between each of the data values and the mean, divided by n, the number of values. The standard deviation is the square root of the variance. Now, I'm a mathematician, and the first time I read this definition, I had to scratch my head and read it a couple of times. So don't worry if you also think that sounds a little bit confusing. Let's look at an example so we can see it in practice. Two leading pitchers in Major League Baseball for 2013 were Clayton Kershaw of the Los Angeles Dodgers and Felix Hernandez of the Seattle Mariners. Their ERA histories are given in the table below. Now, ERA stands for earned run average, so the lower the number, the better. We're going to calculate the mean and standard deviation for Kershaw's and Hernandez's ERA history. What comparisons between Kershaw and Hernandez can you make based on these numbers? So we're going to focus first on Kershaw. So here we see the ERA history for Kershaw from 2009 up through 2013. And our ultimate goal is to compute the standard deviation. So the first thing we need is the mean. So we are going to add together the ERAs from each of these 5 years and then divide by 5. So Kershaw's mean ERA over this time period is 2.47. All right, step 2, in our chart, we are going to make a list of our data values. So in this example, a list of the ERA given from each year. Now, in the middle column, we're going to take each of those values and subtract them from the mean that we found. So in this example, we're going to subtract each of the data values from 2.47. So there's our first value. We did 2.79 minus 2.47 and got 0.32. And then we would subtract 2.91 minus 2.47. We get 0.44, so on and so forth. So we subtract each of our data values from the mean. And now, in the third column, we're going to square each of those values. So we take each of the differences that we found and square them. All right, we're almost done. Now we're simply going to sum the values that we found in the third column. So we add those 5 numbers together. We get 0.746. And then to compute the standard deviation, we're going to take that sum, we're going to divide by the number of values in our list, which in this example is 5. So we take the sum, divide by the number of values, and then take the square root. So we get a standard deviation for Kershaw of 0.39. Great. So now let's repeat this process for Hernandez. So for Hernandez, and you may want to pause the video so you can kind of work your way through and practice this one on your own. So the first thing you want to do is to find the mean. So you may want to pause to find the mean. There it is, 2.87. And now we're going to fill in our chart. So you start with just listing the values in your data set. So in this example, it would be the ERAs given over the time period. And now pause the video and see if you can complete the chart. So you want to subtract each of those values from our mean of 2.87, square each of those answers, take the sum of the values in the third column, and then divide by n and take the square root. So here are your answers. So we do our differences in the middle column, and then square those values, sum the values in the third column, and then to get the square root, we divide by the number of values in our list, which in this example is 5, and take a square root. So the standard deviation for Hernandez's ERA would be 0.43. All right, now what does this mean? So how can we understand these values? Well, because Kershaw's mean is smaller than Hernandez's mean over this period, it means that Kershaw had a better pitching record. But also because Kershaw's ERA had a smaller standard deviation than that of Hernandez. That tells us that Kershaw was more consistent. His numbers are not spread as far from the mean. So the mean tells us Kershaw had a better pitching record. The smaller standard deviation tells us that there's more consistency there. Now, why is the standard deviation a measure of the spread of the data? Well, keep in mind that the mean is a measure of the center of data. And then when we take the difference of the data values from the mean, we get a measure of how far each is from the mean. If the value is negative, the number is to the left of the mean, and if it's positive, it's to the right. But all we want is a measure of how far the number is from the mean. So to make the deviations positive, we square them. Now, the further it is away from the mean, the larger the squares will be. Summing all of these squares will give us a measure of the total spread about the mean, and then dividing by the number of data values gives us an average spread. But since we squared those deviations to make them all positive, our answer has the wrong units. So we fix this by taking the square root and arrive at the standard deviation as our measure of spread. Now, what do you think? Suppose you are a conservative investor. Comparing records of investment advisors, you find that both have a record of earning money for investors. The mean amounts earned are the same, but the standard deviation in amounts earned for advisor 1 is much larger than that for advisor 2. Which advisor would you choose and why? What do you think? Well, one possible answer is to say that because the standard deviation is a measure of the spread of data, a large standard deviation in earnings for advisor number 1 means that many customers experience earnings that are much different from the mean. And that makes it difficult to judge how your own investment will prosper. In contrast, the small standard deviation for advisor 2 tells us that most customers' earnings are near the mean. As a new customer, I have good reason to expect that my earnings will also be near the mean. And so a conservative investor would choose advisor number 2. Let's move on. This figure shows the distribution of heights of adult males in the United States. Now, a graph shaped like this one resembles a bell, which is why it is called a bell curve. And this bell-shaped graph is typical of normally distributed data. So if the data is normally distributed, the graph is a bell-shaped curve. The mean and median are the same. Most of the data tend to be clustered relatively near the mean, and the data are symmetrically distributed above and below the mean. Now, the 68-95-99.7 rule tells us For data that arise as measurements that follow a bell-shaped pattern, you can expect about 68% of the data to lie within one standard deviation of the mean, about 95% within two standard deviations of the mean, and about 99.7% within three standard deviations of the mean. Now note that the 68, 95, 99.7 rule holds approximately for many distributions of numbers, but it holds exactly for those that follow the normal curve. Here is an illustration of the 68, 95, 99.7 rule. So 68% of values are within one standard deviation of the mean, 95% are within two standard deviations of the mean, and 99.7% of our values fall within three standard deviations. Let's look at an example. We noted earlier that adult male heights in the United States are normally distributed with a mean of 69.1 inches. The standard deviation is 2.65 inches. What does the 68, 95, 99.7% rule tell us about the heights of adult males? Here's our solution. We know that 68% of adult males are within one standard deviation of the mean. So this means that 68% of heights are between 69.1 minus 2.65 and 69.1 plus 2.75. So what we've done is we've taken our mean of 69.1 and simply added and subtracted one standard deviation, which in this example is 2.65. So what this tells us is about 68% of men in the United States are between 5'6" and 5'11". Now, 95% of adult males are within two standard deviations of the mean. So we want to take our mean of 69.1 and add and subtract two standard deviations away. So we get 69.1 minus 2 times 2.65 and 69.1 plus 2 times 2.65. So this tells us that 95% of adult males in the United States are between roughly 5'3" and 6'2". Finally, 99.7% of adult males are within three standard deviations of the mean. So this tells us that we start with our mean and we add and subtract three standard deviations away. And so we get that 99.7% of adult males are roughly between 5'1" and 6'5". Great. So each time we're starting with our mean and adding and subtracting that standard deviation away. Here's a final example for you to try. Consider scores on standardized tests. The data set below gives scores on the verbal section of the SAT reasoning test obtained from the College Board website. What does the 68, 95, 99.7% rule tell us about these SAT verbal scores? Now, there's a lot of numbers on this chart. We only need two of them. We need to know that the mean was 507 and the standard deviation was 111. And we can ignore all of the rest of this chart. Great. So we have a mean of 507 and a standard deviation of 111. So 68% of SAT scores are within one standard deviation of the mean. So 68% of scores are between 507 minus 111 and 507 plus 111. So between 396 and 618. 95% of SAT scores are within two standard deviations of the mean. So 507 minus 2 times 111 and 507 plus 2 times 111. So 95% of scores are between 285 and 729. Finally, 99.7% of SAT scores are within three standard deviations of the mean. So 99.7% of scores are between 174 and 840. Final thoughts. How do we choose a summary? Well, the 5-number summary discussed in our previous video is usually better than the mean or the standard deviation for describing a skewed distribution or a distribution with outliers. But we can use the mean and standard deviation only for reasonably symmetric distributions that are free of outliers. That's all for now. Thanks, guys.